Morning, everyone. Welcome back to our final summer STEM Career Talk series here at Berkeley Lab. My name is Kyla, and I'm an intern here at the lab for the summer in the Experiences and Research program. Berkeley Lab is a Department of Energy research facility innovating in materials, life sciences, energy, and way more. Today's STEM Career Talk will be focusing on geothermal energy, and before I hand it off to my co-host to introduce herself, um, if you want to see our previous talks, please check them out on our website. The link will be posted in the chat, and I'll now hand it off to her to introduce herself.
Hi everyone, my name is Dominique, and I am also an experiences and research intern here at the lab. Kyla and I are very excited to be hosting today's panel. For those who don't know, geothermal energy is a renewable energy source derived from heat produced inside the earth. Geothermal heat has many purposes, whether that's bathing, heating buildings, or generating electricity.
So I'd like to start off by introducing our panelists for today. First off, we have Dr. Patrick Dobson, who is a career geological staff scientist here at the lab. And now I'll turn it over to him to give a quick introduction of himself and a quick explanation of the work that he does.
Thanks very much. So I'd like to start off by just telling you a little bit about myself. Um, I'm a geologist, as you mentioned it, at Berkeley Lab, but I didn't start off that way. When I was in high school, actually, I grew up in New England, and I worked as a farm laborer in the summer, 6 days a week, starting in eighth grade, and decided that's not what I wanted to do with my career. So I decided I really wanted to go to college and learn different things. So I went to a school called Williams College back in Massachusetts, which is a liberal arts school. I ended up changing my career to geology my senior year, and in part because one of the folks that lived in the room right next to mine was a geology major and said, "Hey, you should talk to this professor. He takes field assistants." So I went as a volunteer field assistant 2 summers with him, working in New Mexico, and decided, "Hey, this sounds like fun." So after undergraduate, I came out west. The first time I set foot in California was to go to Stanford, and I got both a master's and a PhD there, focusing on geology. I then continued my studies at Caltech, working on isotope geochemistry there. I had a short stint as a postdoc at UC Santa Barbara as well. And then I worked at a research lab for Unica, which is now part of Chevron. At that point in time, they were the world's largest producer of geothermal energy. And I went from the research lab to their geothermal group and ended up doing geothermal exploration all around the world. I did a little bit of consulting for the Chilean government to look at geothermal resources at the 1999 to 2001, and I joined Berkeley Lab in 2000 and have been here ever since. I spent 2 stints as a Fulbright scholar when I was at the lab, once at the University of Chile, and another time at CICESE, which is located in Ensenada, Mexico. I was the program lead for the geothermal program from 2016 to 2023. I retired from full-time work then, and I've been working now as a rehired retiree at the lab. And this is me at a hot spring in Idaho with bubbling gas right behind me. I'm collecting sample for helium isotopes. So let's see if I get the next slide. So when I was a grad student, I also worked part-time for a U.S. Geological Survey, which is in Menlo Park. And there was an eruption of Kilauea back in 1983, and they needed volunteers. So I came out there and worked at this site. What you see on the right is what they called Camp 2. And we asked, why is it Camp 2? And they said, because Camp 1's under the lava flow, right to the left there. So it was really exciting to work on an active volcano and have blobs of magma flying around and to map these different lava flows. For my PhD work, I worked in Japan. This on the left is some really big bonanite pillow lavas. These are lava flows that occur under the ocean that form these big, thick rinds as the ocean water chills the magma and forms it to a really glassy rind around the pillow lavas. And on the right, we were with a film crew from NHK, which is a Japanese television channel, I was working with a professor there, and we got to fly over what is called the Fossa Magna, which is a big fault running through the main island of Honshu. I was also a field assistant, sorry, a teaching assistant for a number of field camps when I was at Stanford. This is a group of students playing hacky sack in the Snake Range, which is located in the easternmost part of Nevada, right near the what is now the Great Basin National Park. And back then, there was no such thing as the internet. We didn't have laptops. We didn't have cell phones. So you had manual typewriters, and there was no electricity. So we had lanterns to type up reports for the field studies. So it was a very different type of experience, but a lot of fun. So now pivoting to, describe what is geothermal energy. As you heard, we're really using the heat from the earth. We're basically tapping the heat. This is me trying to figure out how to sample this big thermal feature at a place called Little Tatio in the northern Chilean Andes. And what we do is we drill wells into these hot rocks, and there's fluid that circulates through the rocks. The hot fluid we bring up to the surface, and we use that to generate electricity. So the key needs are the resource has to have a source of heat, the hot rocks, some flow paths for the fluids to flow through the hot rocks, and then some fluids. And they can be fluids that are naturally present or introduced, we'll just talk about a little bit later. So geothermal systems currently are not found everywhere all over the Earth. There's hot rock if you drill deep enough, but there are hotter rocks in certain parts of the world due to the geology, the circumstances. So if we have zones of rifting, such along the different oceanic ridges, or rifts in the continental plates, or if we have zones of volcanism associated with subduction or with hotspots, that's typically where we have high heat flow and higher temperatures at shallower depths. And this is just showing you a map of sort of where the squares are where the producing geothermal fields are, and then those pinkish shaded areas are areas with active volcanism. So those are probably the most likely places to find geothermal resources. You can see that a lot of X's located right up here where we are here in California. So just to give you a conceptual model of what a geothermal system looks like, this is for a convecting hydrothermal system where we have circulating fluids. We have some sort of heat source. It could be a magma chamber at depth or cooling volcanic rocks that form a thermal anomaly. These are the white lines are isotherms, or lines of equal temperature. So we have a rising plume of hot fluids that are migrating up to the surface that are expressed in the form of different types of hot springs. We have chloride springs and that are discharging at the surface that are sourced by this geothermal plume. We also have a zone of hydrothermal alteration that forms clay-rich rocks, which we call smectite. And then we have also zones where we have steam coming out of the surface, and those are what we call fumaroles. And so those are some of the key components is basically having this heat source, circulating geothermal fluids, flow pathways, and then in many instances, a clay cap that forms. So you talk about, well, how really significant is geothermal energy currently in the US? The US is the largest producer of geothermal electricity in the world, and we have the world's largest producing geothermal field known as the Geysers, which is located here in Northern California. These are just two plots from Bloomberg report. On the left, you can see electricity generation by different sources of fuel, coal, natural gas, and renewables. So renewables are there in the blue color, and you can see that they've been increasing from 2012 to 2024. They've more than doubled in terms of their contribution to the U.S. electricity generation grid. If we just look at subset of what are the renewables, this tiny little line on the very top of each of these bar graphs is what geothermal is. So it's just a small component of this fairly small component here. And so the question is, how can we make it better and bigger? Because you can see that solar's gotten a lot bigger, wind's got quite a bit bigger, and yet geothermal has pretty much stayed the same. So if we look at the different types of geothermal resources, what's been tapped to date pretty much are what we call natural convecting hydrothermal systems. And we currently have about 3.5 gigawatts of installed geothermal capacity. Identified hydrothermal resources are on the order of about 9 gigawatts of power potential. This is a logarithmic plot. So if you notice 10 to 100 to 1,000. We have about three times the amount of identified resources, what we call undiscovered hydrothermal, the ones that don't have a surface expression. And then if we look at enhanced geothermal systems, which are located here, where you have hot rock, but you don't have circulating fluids due to probably an absence of fractures that are permeable, allowing the fluids to circulate, we have many more times. So we have like 500 gigawatts estimated by the U.S. Geological Survey of EGS resources. And so this is what we're really focusing our attention on is trying to open up this potential resource type. And this is just a cartoon of these different types of resources. Here you can see a lot of natural occurring fractures where you have a regular hydrothermal system. And over here we have what we call enhanced geothermal systems where we have hot rock and we create artificially a series of fractures that we can circulate fluids through and extract that heat. So that's it for my quick introduction. Thanks very much, and I look forward to being part of the panel.
Yeah, thank you, Pat, for giving us a lot of more context. And we're going to move on to our next panelist. So we are also joined this morning by Dr. Harry Elizabeth, a research scientist in the Energy Geosciences Division here at Berkeley Lab. I'd like to invite him to, oh, your camera's already on, and you can continue to tell us a little more about your background and your work.
Okay, great. Thanks a lot. Okay, so yeah, my name's Harry Elizabeth. I'm a research scientist here at Berkeley Lab, and I am a research geophysicist. And if you don't know what that is, then you're not alone. I did not know what a geophysicist was when I was in high school either. So just to give you a little bit of a background about how I found myself here, I'm originally from New York, a little town called Cold Spring Harbor. Go Seahawks, which is somewhat famously the home of Cold Spring Harbor Labs, which is where Watson and Crick decoded the structure of DNA. And after high school, actually, or early in my life, I always sort of had some interest apparently in being a scientist. These are some little snippets that my parents have sent me from my early school days. So I guess I had some inkling at an early age that I was interested in being a scientist. But actually, in between high school and college, I took a gap year to go play music with my band and travel around Africa and learn how to drum. So the important thing to realize is that career paths do not need to be in a straight direction. There's plenty of exploration you can have along the way. But after I got back from my gap year, I moved to Rhode Island, where I attended school at Brown University, and still honestly was not too familiar with geosciences, but lucked into a class with a professor with a wonderful mustache featured here. That was actually about the geology of terrestrial planets. So what the geology is like on Earth-like bodies in our solar system, mostly the moons of outer planets. And I thought it was so interesting. I ended up in another geoscience class and another geoscience class, and then it turned out that I had found something of a passion and started doing internships, working in labs just around the university, and that after graduating, actually got a job as a research assistant at a lab in at the University of Maryland, which moved me down to Washington, D.C., and where I ended up joining the lab to do my PhD. Go Terps. And that PhD was actually studying carbon mineralization, which is the process of uh, gaseous carbon dioxide interacting with rocks to form solid carbonate minerals. And this primarily happens actually, in hot water underground. So I was learning a lot about the sort of chemical alteration that happens via hot fluids in the subsurface. And that was sort of my introduction to the world of hydrothermal and geothermal alteration. And then after my PhD, I ended up moving to California for a brief postdoc at Stanford, and then a second postdoc here at the lab, which is where I have had my career to date. So the at the lab we sort of wear a lot of hats. We always do a diverse amount of research, but the geothermal research that I do, um, is I guess you might call me an indoor geophysicist. A lot of geophysicists are around digging trenches, installing seismometers, and things like that. But what I do is I use a lot of the technical capabilities that we have here at the lab to study the sort of fundamental small scale processes that control what is going on in the subsurface. And that has to, this here's a little schematic of pumping some cold water into the subsurface and harnessing the energy in the hot water. But the things that are going on in the subsurface are the evolution of microstructure, fluids moving around, chemical interactions, the formation and closure of fractures. And all of those things have really interesting and subtle aspects that we study here at the lab. And by understanding those things better, we can not only better understand existing resources, but potentially improve the way that we can harvest those resources for the future. Pat briefly introduced the concept of enhanced geothermal systems, and those are places that you have hot rocks, but you need to generate fractures and pump your own fluid down there. And in order to do that, you need to have a pretty good understanding of how that system is going to operate and how it's going to evolve as you change things like the stress and things like the chemistry. And so we do this by taking materials that are actually from these active geothermal reservoirs. So when they're making the geothermal reservoirs, not only the wells that they're using for the process itself, but they often drill additional wells for monitoring or to check out just sort of what sort of materials are down under. And we can get recovered materials from those wells and then use the sort of tools that are available to us at the lab to look at the specific properties of those materials. And so we'll cut them into little core samples so that we can study their structures and compositions in greater detail. So on the left here is a core sample that I use for doing mechanical testing. So, squishing and squeezing the rocks to see how they behave. And then on the right is a close-up, what we sometimes call a photomicrograph, but that is a zoomed in slide of a very thin slice of the rock so that we can look at the mineral structure in greater detail. So my scale bar here is labeled in pixels, but we're looking at just 2 or 3 millimeters across in here. So you can really see how the structures of the rock are interesting at that fine scale. There are different minerals, there are fractures, and those things all are important to understand to be able to predict the behavior of these materials. And so, the way that we test these materials is by, squeezing them to high pressures like they would be actually seeing in the subsurface and seeing how they behave. So here's an example of catastrophic failure due to squeezing a rock, but you can understand a lot about the behavior on the way to that catastrophic failure. And in fact, the way that we do this is a little bit more controlled than that GIF. We'll load up the sample. You can see a big hydraulic press here on the left, and on the right is a close-up of our sample assembly. So that the core sample of the rock is actually inside a rubber jacket here, and you can see all the wires coming out. We instrument the rock with all sorts of different sensors so that as you're squeezing it, you can understand how things are changing in the rock system. We can look closely at the way that the rocks are changing, like for instance, the way that the fractures are forming and closing as you increase the stress. And you can measure how the properties change. So here is a plot of what's called the elastic modulus, or how stiff the sample is, as a function of pressure and temperature. So we can make these kind of maps that show as you change the temperature, as you change the stress in the subsurface due to flowing fluids through it, due to changing, pumping high pressure fluids in it, you can uh, actually change the way that the materials are behaving. And by mapping that carefully in the lab, we can then better understand how the reservoirs are going to operate underground. Another really interesting thing that I do here at the lab is use the advanced light source, which is our synchrotron facility, which is a big machine that generates X-rays. And then we can use those X-rays to actually image how these rocks are changing at high temperature and high stress. On the right here is another example of one of those pressure vessels that you can use to put materials at those conditions that they would be seeing in the subsurface. And that allows us to make maps of the structure. So here is, one of those core samples imaged in the high pressure condition using X-rays. And I've highlighted here what the fractures are within the rock. And then we can use different kinds of digital tools to simulate, for instance, how fluids are flowing through the fractures that exist in those rocks. Um, and we can also dynamically change the environment. Here is some more of that interesting in situ X-ray data that shows what are called proppants, which are basically granular materials, so grains of sand or little ceramic balls that you can put into the subsurface that will hold open fractures as stress is changing. And that is one way that you can ensure that you can continue to flow fluids through the subsurface as the stress is changing, which is a really important aspect of enhanced geothermal systems. And that's pretty much just a few examples of the sort of techniques that we use to explore the fine scale behavior of the materials that you would find in a geothermal reservoir. And I think that is all I have. So next up, I believe we'll take some questions.
Yeah, thank you so much for sharing. I love the use of the GIF and the diagrams of the machinery. So now we'll be moving on to our Q&A section of the program. So I'd like to invite everyone to turn their cameras on and encourage our audience to add some questions to the chat box. And we'll start off with some questions that we've created.
Great. So starting off, how does geothermal energy compare to other renewable energy sources in terms of cost and efficiency? So like wind, solar, hydropower. We can start with Harry and then Pat.
I think maybe this is a better question for Pat to answer. He's got the long-term perspective here.
Sure. So, a couple of things. One of the important aspects of geothermal energy is that it's 24/7 available. Wind and solar have the challenges of being intermittent in when they're generated. So at night there's no solar energy. When there's no wind, there's no wind energy as well. So that's an important distinction. The other thing is that geothermal energy, because it's under the ground, there's a bit more risk and a bit more uh, time to identify and find those resources. We know where on the Earth it's sunny and where on the Earth it's windy because we have stations that measure the weather and we know how many cloudy days there are. So there's a lot less risk involved in terms of identifying where are good places to put solar panels, solar arrays, or wind farms and they can be built very quickly. So in a matter of a couple of years, the wind farms or solar farms can be installed and working in like 2 years. Geothermal typically takes about 7 years to go from when we start drilling a well to when we actually are producing power. And there may be instances where we drill wells and we find that the resource really isn't what we thought it was because it's in the subsurface. So some of the things that our team at Berkeley Lab is working on is trying to improve our ability to characterize the subsurface and reduce those risks and shorten the timeline it takes to develop geothermal resources. Our group also has done a comparison of the costs for geothermal power versus wind and solar, and it's still a little bit more expensive than wind and solar. But once again, because it's available 24/7, it has higher value because you need to be able to store solar energy to be able to produce it at night.
Yeah, I think the note of geothermal energy being available 24/7 is a really big advantage compared to other resources. And moving on to our next question, what types of geological conditions are ideal for geothermal energy production? And how do you monitor and manage the environmental impacts of geothermal drilling?
Sure, I can take a start, and I'm sure Pat will have a perspective on it as well. So the ideal place to harvest geothermal energy, as Pat stated, are what are called hydrothermal systems. So those are places that you already have hot fluids that are circulating easily through hot rocks. And so if you've ever been to like a natural hot spring, those sort of environments are the best sort of environments. The fluids are abundant, they're easily circulating, it's easy to get to, it's easy to identify. So that's sort of your ideal candidate region. Um, and but the sort of frontier of geothermal right now are these enhanced geothermal systems, because there are many, many more regions in the United States and in the world that you have hot rocks, but not necessarily actively circulating fluids. And the technology has been sort of developing such that we can engineer the ability to flow fluids through those rocks more and more easily these days. And so I would say the potential for being able to deploy geothermal energy is growing, and it has a lot of opportunities in the near term and sort of in the midterm as well.
So great. I guess I'll try and answer the second part of that question, which is looking at the environmental impacts and how to mitigate those. So some of the ways the impacts that people are concerned about are the emission of different types of gases. A lot of geothermal areas are associated with H2S, which is sort of the rotten egg smelling gas. You also have CO2 and other gases. So one of the ways that we can do that is if we used a closed loop system, and these are what we call binary power plants, where we're basically bringing up the hot fluid as a single phase fluid and using a heat exchanger to heat a secondary working fluid that then powers the turbine. And that way, those gases never are released to the surface and they're just re-injected back into the geothermal reservoir. In other instances, there's a place in Iceland that's been doing this. They're capturing the CO2 and capturing the H2S, and they're re-injecting it back into the subsurface and creating mineral forms of those phases, so that CO2 then forms different types of carbonate minerals in the subsurface. And so that's another way of sort of sequestering those gases without having them go into the atmosphere. Another topic that our lab's been working on for a lot of times is the issue of induced seismicity associated with geothermal power plants. And so if you're ever up at the geysers area, this is in Northern California, Sonoma County, Lake County, Mendocino County, that area. There's a big area of geothermal production. It's still the world's largest geothermal field. It's been producing since 1960, still generating about 850 megawatts. But there's quite a bit of seismicity associated with the reinjection of fluids back into the reservoir. And why do we reinject the fluids? There are two reasons. One, in liquid dominated systems, those fluids are brines that have a lot of sort of components that we don't really like. And so we want to put them back into the reservoir so they don't contaminate groundwater. The second thing is by putting it back, it recharges the reservoir. If we were just to remove the fluid and not put it back, the reservoir would dry out and we wouldn't be able to extract the heat. And so that's a really important component of how to manage these systems. So what we've been working with is monitoring the seismicity associated with reinjection of geothermal fluids and developing ways to reduce their impacts by relocating injection or reduce the amount of injection in a single well or making sure that it's not near any active faults to really try and not have significant seismicity occur in the vicinity of the geothermal power plant. So those are two of the main concerns. Other issues could be, discharge of fluids, but that's really just making sure you don't do it. And then another impact is visual impact. You'll see these power plants and pipelines. You wouldn't want to put geothermal power plant in the middle of Yellowstone National Park, which is a really vibrant geothermal area, just because it would not look good, and it would also impact the activity of those natural geothermal features. So if the way sort of the benefit of what these resources are in terms of natural beauty versus power production.
I think that's actually a really interesting topic as well, because that has a lot to do with the sort of social and political interaction. What a geothermal plant should look like and be used for is something that is sort of determined communally by a community. For instance, in Iceland, they have a geothermal power plant, and the outflow pool from that power plant happens to make this milky blue liquid that has turned itself into something of a tourist attraction. People like to go and bathe in it. So, they turned what, might otherwise have been a waste stream into, something that became a resource.
Yeah, they charge $50 a head for people to go there. They make more money off of the Blue Lagoon than they do from the geothermal energy they generate at the power plant. It's pretty remarkable.
Yeah, it sounds super cool that we're almost able to like create these new opportunities for like within geothermal energy, like Harry said, with injecting like liquid with the hot rocks. And that almost makes me want to go visit the hot lagoon too. But I'm gonna move on to one of the questions from the chat. What other jobs are there in the geothermal field that you are both interested in? And do you see research careers growing?
Well, I'll take that a little bit. I mean, I would say, geothermal energy is a really exciting industry. And research careers, I would say, are actually like relatively stable because, in fact, the technology has become mature enough that most of the growing jobs are actually industrial careers. There are private companies that are doing geothermal now that are growing actively and presenting lots of opportunities. And that's to do the sort of technical work that Pat and I have been talking about here, assessing geology, looking at the properties of rocks and things like that, but also all sorts of additional roles that are important for companies like that. Uh, Leasing land. These geothermal reservoirs are mostly on federal land, and so um, like interacting with the government and all of the aspects of that are really important aspects. They have all of the things that you would have in any company. They have administrative roles, they have HR, there are just new and more growing jobs if you're interested, but not necessarily, so fascinated by the technical side of things. There's actually a big diversity of careers that are available in the geothermal industry.
And just sort of to follow up on that, one of the key, really exciting parts of Berkeley Lab is the incubator called Cyclotron Road, which basically encourages young or investigators with new startup ideas to apply to join the program. And two of those cohorts from Cyclotron Road have created companies associated with geothermal systems. One is called Zanscar, the other one is called Fervo. And Fervo is in the process of revolutionizing geothermal by really making EGS cost competitive with other types of energy sources. They're in the process of developing a 500 megawatt resource in Nevada, adjacent to a Department of Energy test bed called the Forge site. And I was out there last month. They are in the process of developing the first 100 megawatts of power from that facility that's going to be coming online next year, and then another 400 megawatts that's going to be coming on in the subsequent years. So that sort of aspect of career development, these companies are really starting to take off. A lot of people who worked in the oil and gas industry have the same sorts of skills in terms of characterizing the subsurface as geologists and geophysicists, as drilling engineers, as reservoir engineers. There's a large type of a range of different types of skill sets that can be applied amongst many different disciplines. And so that's one of the exciting things as well, is looking at repurposing people who are working in different sectors into the geothermal sector.
Yeah. I think there are a lot of misconceptions that like certain fields don't have a lot of job opportunities, but I think it's great that students get to hear from you guys that are actually many career paths that are growing, especially in the geothermal field, if you have the skills to apply them with. Moving on to our next question, what kinds of tools or machines are being used to understand the formation and evolution of geothermal systems, and what type of innovations have been made in the past years to enhance your research?
Sure, maybe I'll take that one to start. So there are all sorts of things. I mean, there are some of the sort of lab-based tools that I talked about in my presentation, which are using X-rays to understand the composition and structure of the rocks, using large hydraulic presses and sensors to look at how the mechanical properties of the rocks are changing and things like that. But all of that actually works in concert with similar and analogous tools that we use in the field themselves. A lot of the sort of standard toolbox of the geophysicists, which are, seismometers, which are sensors we use to study earthquakes, and electromagnetic tools that can look at the way that electricity interacts with the rocks in the subsurface as well. Um, Other sorts of chemical tools that you can use when you sample fluids coming from the reservoirs or gases coming out of the reservoirs, mass spectrometers, things like that. All of those tools sort of like work together in order to understand fundamentally how these reservoirs are behaving and how they're changing as the geothermal reservoir is developed or operated.
And then sort of to build upon that, once we collect a lot of different types of field data from these geologic mapping and geophysical surveys and then drilling wells to get a better idea of what the subsurface conditions are like in terms of the geology and the pressure and the temperature and the types of hydrothermal alteration. We typically build what we call numerical models, and these are basically computer simulations of the different types of processes that are occurring in the subsurface. And so we build these reservoir models that can be used to sort of understand and to optimize the performance of a developed geothermal system. So we're looking at transport of heat, transfer of fluids, water rock interaction, geochemical reactions, geomechanical processes. These are all sort of included in these computer models that we've developed. And we've been doing this at Berkeley Lab since the 1970s.
Yeah, and one advancement that has been happening recently is, as we push the frontiers of enhanced geothermal, we're looking at higher and higher temperature resources. And so developing the sort of sensors that are used in conventional reservoirs that can be used at more extreme conditions, higher temperatures, higher pressures, maybe more corrosive chemistries, is really essential in being able to get the information we need to operate those reservoirs. And that is some work that we do here at the lab in terms of developing high pressure and high temperature sensors for deploying in the field, and working with partners in industry and at other national labs for that kind of work.
Yeah, it's super cool how like advanced we've become in being able to see all these um like environmental or geological factors and also being able to model them like Pat said. But I'm gonna move on to a question from the chat. Pat, you showed a lot of different places in your slides, and people were wondering, did you get to visit these places that you traveled to, or were you mostly staying within your work?
So that's one of the great things about being a geologist, a field geologist, is you get to go out of the lab and spend a lot of time in the field. And so I've worked and visited geothermal systems in many parts of the world. We had a project recently in Iceland. I mentioned I did my master's work at a geothermal system in Mexico, at a place called Los Azufres. I've done geothermal exploration throughout Mexico, Guatemala, El Salvador, Nicaragua, Costa Rica, Chile, visited sites in Argentina as well. I spent probably 8 months working in Indonesia, looking at geothermal systems there. I visited geothermal systems in Japan. So where there are hot rocks and interesting places. Also worked on a project in Kenya. Over about 25% of Kenya's electricity is generated from geothermal power plants in the East Africa Rift. So there are a lot of really great places to go around the world, and it gives me a great excuse to go and travel and visit these places and study them.
Yeah, and even as a an inside geophysicist, as I call myself, I do have the opportunity to travel in order to understand the broader geological context of the sample and also just to collect samples to be analyzed. And so I also have been on trips to Iceland, all around the western United States, to Utah, to Nevada, and even to northern Norway to look at some of these naturally hydrothermally altered rocks. And yeah, while you're there, I mean, well, geologists are self-selecting, and so you're probably more likely to find them out on the side of a mountain than at the, whatever large city is nearby. But you do need to fly to those cities as well. So it presents a lot of opportunities for cultural as well as scientific experience.
Yeah, I feel like you guys definitely get to see as well a much bigger perspective of the world through your work. And we're going to move on to another question from the chat. Could geothermal energy advance enough to become the primary energy source, considering its high upfront costs or geological constraints?
So I would say for the US, it's never going to be the primary source. In some countries, it is already. So if you go to a place like Iceland or you go to a place like New Zealand, very large portion of their power generation is through their geothermal resources. In the US, it's less than 1%. In California, California is the state with the largest amount of geothermal generation because we have large abundance of resources. It makes up a couple of percent of our power generation. What we're looking at a study that the DOE carried out, which is something called the GeoVision study. And if we were able to lower the cost of EGS, and they've come down considerably over just the last 4 or 5 years, there's something called the Earthshot that the DOE has implemented to really try and reduce the costs. It could result in 5 to 10% of the total power generation in the U.S. coming from geothermal energy. So it would still be, not a major source, but an important component of the power generation in the United States. In other countries where you have more geothermal resource, more concentrated resources in places that are geologically, ideally located, such as a place like Iceland or a place like Kenya or a place like New Zealand, that percentage could go significantly higher.
Yeah, and I think that something that's really important is that, it's likely that the future of energy generation is going to be a lot more heterogeneous than the past of energy generation, and that geothermal has some important aspects, which are its, ability to provide constant power as opposed to intermittent power, which is a really important aspect of it, and also the ability potentially to apply deployable power, which means not only can it constantly produce energy, but it could potentially change the amount of energy that it's generating in response to demand, which is not necessarily something that's capable from other renewable sources. So it really plays, I think, an important and unique role in the energy future.
So one other thing, just to add on that, that is sort of overlooked is, in addition to generating electricity, it can be used as a lower grade source of energy for heating and cooling purposes, which is a huge part of our energy budget that people don't really think about. And so that's an important thing. And then secondly, it can be used as a source of energy storage. So you could have seasonal storage where you don't need energy for heating. You store hot water in the subsurface. You basically use it to cool data centers, which are growing more and more with the increased use of AI. And then in the wintertime, you could tap into those stored hot water to use for district heating. So just being creative about how we use the subsurface, it could expand how geothermal is used in addition to just power generation.
That sounds like geothermal energy um, is looking to play a really big role in the near future, and I'm really excited to see how that works out. But one of our audience members wanted to know more about the first class that got you interested in geothermal. I think this is for Harry. You were talking about how you were into the moon and surfaces of other planets. So I guess they're wondering, would it be possible to get energy from those planets as well?
Well, I mean, that first experience I had in the class was just sort of a gateway to geology that I became fascinated with the diversity of structure and composition that you see. And actually, the amazing insight that you can gain on the dynamic geological processes that are taking place on all these different bodies just from satellite photos and people thinking really hard about how you could possibly come up with the really interesting forms that you see when you take pictures of these places. Um, but to answer your question, I would say actually geothermal energy is likely an important component of what energy generation will take place if and when there is, extraplanetary exploration. As Pat was saying, you can actually leverage temperature changes in the shallow subsurface as a way to really efficiently heat and cool, which is an important energy sink when you have any kind of building going on. And so leveraging those kind of capabilities will almost certainly be an important aspect of developing long-term scientific bases and things like that on the moon and potentially on other planets. I mean, many of the moons of other planets are volcanically active, which means there's ample geothermal resource. And uh, I don't know, several centuries on, when we've got some sort of base on Io, then it'll probably be geothermally powered. But now we're venturing into the realm of science fiction.
So in terms of how I got involved with geothermal, it was sort of a little bit of serendipity. My master's thesis was looking at studying a young volcanic center in Mexico called a place called Los Azufres, and it was co-located with an active geothermal system that the Mexican government was in the process of developing at the time I was there. And for me, the geothermal system was an annoyance because it's altering my rocks that I want to alter. I want to analyze really fresh volcanic rocks, and here I've got all this clay alteration and from the active geothermal system. So I'm looking at it as sort of a nuisance. And so during that summer, there was a joint conference between a group called Comisión Federal de Electricidad, which is the Mexican Federal Commission of Electricity, and the US DOE, with a lot of people from Lawrence Berkeley National Lab attending. And so I was asked to be a translator for a field visit to two geothermal areas, Los Azufres and La Primavera. And one of the participants on that field trip was a geochemist from the U.S. Geological Survey. His name was Alfred Truesdale. He's one of the sort of the key developers of chemical geothermometers for geothermal systems. And he was like, "What are you thinking? You should be doing both. You should be looking at, come to my lab, here are a bunch of sample bottles, collect some fluids." So my thesis doubled. And it was just through the serendipity of meeting this inspiring scientist who welcomed and encouraged me to really reach out and embrace the geothermal component of what I was studying as opposed to just focusing on the volcanology. So it was sort of this chance encounter that changed my career. So it's really neat to have these types of experiences and to open yourself up to making these changes.
Yeah, there's a lot of seemingly small experiences that we have throughout our lives that can really change the trajectory of what we find interesting and what we want to do in the future. And speaking of some experiences, one of our experience in research interns are using Tough React, and they're wondering if either of you use this in your computer models.
Absolutely. So when I first came to Berkeley Lab, I was basically given the job of using Tough React for the challenge of monitoring uh, the reaction of storing high level nuclear waste. And so what we wanted to do was to see if we are heating the rocks by putting nuclear waste. Basically, the decaying nuclear waste is going to be a sort of artificial heat source, and it's going to, if you're putting it in a geologic repository, it's going to provide heat to the surrounding fluids in rocks. And the question is, how would that impact the behavior of those fluids and rocks in terms of changes in mineral chemistry, sealing or dissolution of minerals. And so one of my colleagues here at Berkeley Lab was doing some laboratory experiments, and I was asked to use Tough React to model those experiments. And so uh, it gave me the excuse to then step out and use active geothermal systems such as Yellowstone, looking at cores and fluids from Yellowstone as an analog, natural analog for looking at changes in fluid flow and permeability associated with these water rock interactions. So Tough React was a really important component of some of my early research at Berkeley Lab.
Well, while we're on the topic of like heating and all of that, we were wondering, has adverse weather like flooding, higher temperatures, or even droughts caused a shift in the amount of stress that has been put on materials studied in the geoscience field?
Well, I would say actually, geothermal energy is probably one of the most robust sources with regard to those sort of environmental factors. But a really important
Harry's frozen. Are you guys hearing anything more from him?
No. Maybe if you wanna try and answer that while he can connect back.
Okay, so here's an example of how these types of issues have actually motivated people to move more towards geothermal, as Harry was saying. The Fukushima disaster in Japan, which was sort of a massive earthquake that generated a tsunami that basically wiped out one of their nuclear power plants on the coast of Honshu, resulted in Japan sort of re-evaluating their reliance on nuclear power. And so as a result, there was a lot more attention being shifted towards the potential of Japan using its natural geothermal resources for power generation. One of the other neighboring areas, Taiwan, also had nuclear power plants on their coast, and they were worried, hey, we don't want the same thing to happen. So they've also awakened or reinvigorated the exploration of geothermal resources as a way of producing power in their countries. So I would say sometimes those types of things impact other power generation sources and basically propel people to look at geothermal because of its robustness.
Harry, if you wanted to continue what you were talking about earlier, I know you cut off.
Are you frozen again, Harry? You're
I
okay. You're
it,
back.
okay, I'm back. So maybe Pat covered this, but what I was mentioning before is that a big challenge for enhanced geothermal system is access to water. You need quite a bit of water in order to make those systems work. So water use is something that needs to be paid attention to in the development of those sort of systems.
So two other types of issues that people worry about that could impact geothermal. One is if you're near a volcano, if you have the volcano erupt, that can pose a problem. And so the Puna geothermal power plant on the Big Island of Hawaii actually had to shut down for almost a year because a good portion of their geothermal field was covered with lava flows. So that's one of the risks associated with being near, putting things near active volcanoes is that those volcanoes can erupt and you have to deal with that. A second thing is wildfires. And here in Northern California, we were always living with the presence of wildfires, and those wildfires impacted the geysers geothermal field several times over the last 10 years, where they basically some of the cooling towers were burned down, a number of the plants were shut in because they had to evacuate the operations staff. So that's another sort of environmental concern that we deal with here in Northern California that does impact geothermal power plant operations just because you can't have the land around you on fire if you're trying to operate the system.
We're going to move on to the last question of our session. So, to both Pat and Harry, what do you wish you had known in high school or early college that would have made your career path a bit easier and less stressful?
Well, I guess I will start, but something that I have learned over the course of my career is, to follow your curiosity and not be intimidated by things that you don't think are qualified or capable to do. If there's a math or an engineering course that you think is interesting applications, but you think of yourself as like a math or engineering person, you know, with like there are people that are there to help you there's, there are different aspects of interesting things that you can get from all sorts of different educational experiences. So even if you're not ace class, you may learn something really that will have an impact on your later career. So, I would say, don't be intimidated or have any kind of preconceived notions about what you ought to be doing or how your brain works. But just follow your interest and your creativity, and you probably will end up all right.
So I guess I would say, you know, don't be afraid to make changes. I mean, I changed my major my senior year, which caused a little bit of stress because I have to take all these other classes to meet the requirements. But it meant that I got to do something that I thought would be really fun. I guess another thing is that, at least in graduate school, I probably learned more from my fellow students than from my professors because we had a really great group of students that shared with each other. I worked as a volunteer field assistant for a number of my fellow students because I felt, hey, I can learn from them. I can see new things. I can really broaden my horizons, and I get to go out and hang out in really cool, neat places across the world. And so, you know, be adventuresome and don't necessarily as Harry was saying, your career is not going to be a straight line trajectory in many instances. So don't be afraid of the zigs and zags. And it's a little scary because you're doing something that maybe you haven't done before, and there's a little scariness, but there's also a lot of excitement as you're learning new things.
Yeah, I think within a lot of young people, they have this idea that they need to know exactly where they're gonna go or what's the next move in their life, and that can, put a lot of pressure when you see like other people and then, they start to compare themselves. But there was actually a comment in the chat and they said that they had no idea what geothermal actually was, but now after this talk, they feel like they want to learn more and see if it might be something that they can go into. And they just wanted to thank both Pat and Harry for this, lovely talk. And I also want to thank our panelists for participating in today's career talk and the audience for being super active today. They asked a bunch of insightful questions that were wonderful. I think Dominique is gonna uh finish us off today.
Yeah, I just want to tell you guys that this career talk today will also mark the last of our 2025 STEM Career Talk series. If you do wish to check out the other career talks or this career talk in the future, they are all available on our website. I'd like to thank you all so much. Have a great rest of both your Friday and your summer.
Thanks again for allowing us to participate. This has been a lot of fun.
Yeah, thanks
Thank you
everyone.
so much, guys.
You.